Residuals play an important role in determining the adequacy of a linear model. It looks like from our correlation coefficient that we have a linear relationship, but there's still a chance that we really don't. So a residual analysis, it's like a post-analysis that tells us for sure, is our model a good linear model or is it not? So we're determining the adequacy of the linear model. In fact, residuals can be used for the following purposes. So there's three things that we're going to be looking for in the residuals. To determine whether a linear model is appropriate to describe the relation between the predictor and response variable. So again, this is a post-analysis. Is our linear model appropriate? To determine whether the variance of the residuals is constant. That's important. We have to have a constant variance in the residuals, and if there's not, there's a problem. And third, we have to check for outliers. If there are outliers in our data, that's a problem. And outliers can show up in residuals. So here's the deal. To determine if a linear model is appropriate, we also need to draw a residual plot. Now, a residual plot is a scatter diagram with the residuals on the vertical axis and the explanatory variable on the horizontal axis. So this problem here, we found all of the residuals. So if I were to create a plot, so I'm going to form a point with 3 and the residual, 0.4, and 5 and the residual, 0.2, and 7 and the residual, -1, and so on. And I'm going to plot those points. That's a residual plot. So I would have x on the horizontal axis, and I would have y minus y hat on the vertical axis. And I would plot those points, and that is what a residual plot is. So if you're going to create a residual plot by hand, which we're not going to do, but if you were going to, you would have to find all of the residuals for every data point. And again, you would plot that so that the x's are along the horizontal axis and the residuals are along the vertical axis. Now, is a linear model appropriate? That was our first bullet. If a plot of the residuals against the explanatory variable shows a discernible pattern, such as a curve, then the explanatory and response variable may not be linearly related. In other words, like if I have my x's along the horizontal axis and I have the residuals on the vertical axis, what I want to see in that residual plot is something like this: no pattern. This is what I want to see, no pattern. If I see some kind of a pattern such as this, down and up like a curve or something, that is a problem. This occurring in the residual plots generally would mean that a linear model is not appropriate, regardless of what the correlation coefficient told us. So if you see any kind of a pattern such as this, that's a problem. Is the variance of the residuals constant? If a plot of the residuals against the explanatory variable shows the spread of the residuals increasing or decreasing as the explanatory variable increases, then a strict requirement of the linear model is violated. This requirement is called a constant error variance. So we have to have a constant error variance, which means, again, we want something like this. As I go from left to right, the spread of the residuals needs to stay constant. If something like this happens, and as you go from left to right, the points get farther apart as you go, or if they start farther apart and get narrower together as you go from left to right, that's a problem. That would mean we do not have a constant error variance, and that would mean a linear model's not appropriate. So this kind of residual happens if our original scatter plot does like this. So this would be like the original scatter plot of the X versus the Y. And so there's more points over here that are spread out than there is over here, and that's an issue. So that shows up in the residual plot like this. So again, basically, we want no pattern, and we want the variance, we want the spread of these points to stay the same as we go from left to right. Third, are there any outliers? An outlier can be thought of as an observation whose response variable is inconsistent with the overall pattern of the data. To determine outliers, either construct a plot of residuals against the explanatory variable or draw a box plot of the residuals. Outliers can be found using a residual plot because these residuals will lie far from the rest of the plot. So like if this is our original data, we have X's and we have Y's. Most of the data are here, but then here's an outlier. So if I find all of the residuals, and if I make a box plot of the residuals, there's the outlier in the residuals. That's a problem. Or if I don't draw a box plot of the residuals, but if I do a residual plot, there's the outlier in that residual plot. So again, the rest of these are pretty well spread out the same, but then you got that one that stands apart from all the others. So if you have an outlier, that's a problem. A linear model is going to be skewed by outliers. We talked about that before. So we don't want outliers in our data. That makes a linear model inappropriate. Now we might choose to remove an outlier from a set of data so that we do have an appropriate model, but we have to be able to justify that. Now it is possible to construct a residual plot, both with our calculator and with StatCrunch. It's simplest to do this with StatCrunch. So I'm going to show you that first. So using the American Black Bear data from the previous sections, construct a residual plot to verify the requirements of the least squares regression model. Comment on the adequacy of the linear model. So I'm back to StatCrunch. So again, I have my Bear data in these two columns. And so here's the deal. When I do stat and regression and simple linear, I choose the X variable, I choose the Y variable. There's nothing new here. Among the options that I have in this list of stuff, one option is I can save the residuals. And so I'm going to select save the residuals. And when I say compute, in addition to finding the stuff that we found earlier, the regression line, the correlation coefficient, the coefficient of determination, the sum of the squared residuals, and all of that, in addition to that, it has now saved the residuals in this column called residuals. So if I were to plug 139 into my regression equation, I didn't get the predicted value, but the residual would be 16.98. So if I took 110 minus the predicted value, I would get 16.98. These are all of the residuals. So I can make a scatter plot using the total length and the residuals in order to see if there is a problem in the residual plot. So I can go to graph and scatter plot. I have my total length for my X variable, and I'm going to use residuals for the Y variable. And I say compute, and when I do that, I get this plot. So this is my residual plot. I have the X's here, and I have the residuals here. So is there a pattern in the residuals? I don't see a discernible pattern. So we're okay there, no discernible pattern. Is there a constant error variance? Do the points stay roughly the same spread as we go from left to right? The answer to that is yes. I don't see a scenario where the points are getting wider or narrower as we go from left to right. So we have a constant error variance. We're good there. Do you notice any outliers in the residuals? There aren't any points that stand far away, like way above or way below the bulk of the other points. So there doesn't appear to be any outliers. Now, I could verify for sure that there aren't any outliers by also doing a box plot of the residuals. I'm going to draw it horizontally and identify any outliers. Here's the box plot of the residuals, and there aren't any outliers. So there's not a discernible pattern. We do have a constant error variance, and there aren't any outliers in the residuals, so we're good. For our bare data, the regression model is appropriate. So that's the residual analysis. Again, you found the regression line, so you find all of the residuals, create a plot, and see if there's any of those three problems in our plot. If not, we have a good model. If there are one of those problems, then our model's probably not appropriate. That's pretty much it for section 4.3. The only other thing that I have in section 4.3 is just a couple of comments that you need to be aware of. And that is, beware of influential observations, which may or may not be outliers. Most likely they will be outliers, but possibly not. An influential observation is an observation that significantly affects the least squares regression line's slope and or y-intercept, or the value of the correlation coefficient. So I mentioned this to you before when we were first talking about correlation and the fact that correlation's not resistant. So if here's the set of our data, and pretend at first those three cases aren't there, right? So that would look like a linear model's probably appropriate. But if you have a point over here, the regression line is going to get pulled towards that point. So that's going to mess up our model. So we have to be aware of that. Similarly, case 3, same kind of deal. That point's down over here, so our regression line is going to get pulled towards that point. So that's going to mess up our model. And then the third possibility is it may be over here. And so more of a problem is whenever maybe we don't have much of a relationship, but then you got a point over here like that, and it makes it appear that there is. We get a higher value in the correlation coefficient than maybe should be warranted. So we have to be careful of that. In any of these cases, the regression line is kind of pulled towards those influential observations. And then just an example of that, if we use our golf data and we include like a professional like Justin Thomas, he swings 120 miles per hour and the ball travels 305 yards, so we get this influential observation. Without that point in the data, the blue line is the regression model. But if you include that point in the data, the model gets pulled towards that point. That's an influential observation.